This is section 4.6. In this section, we're going to be using the ideas that we developed in the previous section to solve polynomial inequalities and solve rational inequalities. The first part of this video will deal with solving polynomial inequalities. Okay, so let's get thinking about how to solve polynomial inequalities. So they give us some guidelines here for polynomial inequalities on how to solve them. They encourage us to first move everything to one side of the inequality, the left side or the right side, whichever side works for you. Most of us tend to read left to right, so it's easier to move things to the left. And then solve for x to find the x-intercepts of the polynomial. Then you're going to create what are called test intervals. The test intervals come out of the x-intercepts that you found. And then you're going to grab test points from each interval, plug it back into the original inequality, and see if it satisfies it. And your answer will consist of all the intervals that satisfy the inequality. And you're going to have to use interval notation to express your solution here. Okay, if you notice here, I already sort of sketched some graphs here. There's some stuff going on. I'll explain to you what it is that I did. What are these graphs saying here? But let's, in a sense, these graphs kind of are answering the inequalities. But in order to understand what these graphs are saying, let's first go through the process of solving these polynomial inequalities first by hand, and then we'll talk about what the graphs are saying about the polynomial inequalities. Okay, so at this point, if I was you, I would take the challenge of trying to solve these polynomial inequalities by myself. So pause the video, take a few minutes, see if you can solve each one of these inequalities, and remember, your answer should be in interval notation. It should be a set of intervals that satisfy the inequalities. Okay, so hopefully you had a chance to solve these inequalities, and let's compare answers. And let's compare the procedure to get to the answers. Okay, so the first thing I'm going to do in order to start solving this inequality right here, the first one, is that I am going to, in a sense, set it equal to 0. I'm going to set it equal to 0. Even though we're dealing with an inequality, in a sense, what I'm doing is I am putting all of my terms on the left-hand side, and on the right-hand side, I use 1, 0. So then that means that I'm going to subtract x, I'm going to subtract x, I'm going to subtract a 3. Okay, and so then I end up with this inequality. X squared plus, oops, it's not 3x anymore. So x squared plus 2x minus 8 is less than or equal to 0. Yeah? Okay. And then, furthermore, what I'm going to do, sometimes this is not possible, but if it's possible, so now that I have everything on the left-hand side of my inequality, I am going to try to factor the left-hand side as much as possible. And what I notice is that this can be factored in the following form. It can be factored like this. X plus 4 times x minus 2 is less than or equal to 0. Okay, and so now it turns out that I have 3 sets of inequalities here. I have the original inequality, I have this inequality that is less than or equal to 0, and I have this one where I factored. Turns out that the solution to either of them, they all should have the same solution. All of these 3, so these 3 inequalities are equivalent. So whichever one I solve is also a solution to the other one. So they all have the same solution. Alright, so I would say that that is the first step to take. Sort of set your inequality equal to 0 and try to factor as much as possible. Then the next thing I'm going to do is I'm going to find the zeros. Alright, so what that means is I'm actually going to have to set my inequality equal to 0. Or rather, this expression on the left-hand side, I'm going to set it equal to 0. So I'm going to say x plus 4 times x minus 2 equals equals 0, and well, what that should imply is that I have two solutions. X equals -4 and x equals 2. Okay, so those are my zeros. And now what I'm going to do with them is that they, in a sense, what they do now is they create intervals. They create intervals in the Cartesian plane for me. These are called the test intervals. So we're going to say test interval. And well, it turns out I have two intervals. One of them is from -infinity to -4 union 2. Or sorry. So -infinity to -4, -4 all the way to 2, and union 2 to positive infinity. And actually, I need to be careful here. I should, if you notice the type of inequality that we're dealing with, this is not a strict inequality. This one is less than or equal. So instead of using parentheses here on my inequalities, I should actually be using brackets. So let me correct that. Let me just change to the eraser here, whenever that works. This should all be brackets. So the only things that should be parentheses are the things that are -infinity and positive infinity. Otherwise, I'm dealing with brackets. So let me change things to brackets. So I need to erase these parentheses, but as you know, the story of my computer, it slows down whenever I'm recording videos, and it's difficult for me to change from pen to eraser and vice versa. There we go. So this should actually be brackets. Let's see if I can go back to pen. All right, so that's good. So that's a bracket. This is supposed to be a bracket. And again, the reason why these are brackets is because of the type of inequality that I'm dealing with. In the next example, we should be using parentheses because that's a strict inequality. All right, so these are my test intervals. And now what I'm going to do is from each test interval, I'm going to grab a test value. And the way I pick my test values is I just try to make my life simple. And so then, for instance, from this interval, -infinity, so from the interval -infinity to -4, I am going to pick a test value. So I might say, I don't know, x equals -5. From this test interval, I'm going to pick a value too, an x value. I don't know, let's say x equals 0. From this test interval, I'm going to pick a value. I don't know, let's just say x equals 3. Yeah? All right, so I pick some test values. And now with these test values, I am going to plug them back into my original inequality. So these test values, I will plug them back into my original inequality and see if it satisfies the inequality. And you might be thinking, well, I have 3 versions of the original inequality. Which version should I pick my test values? Into which version should I plug in my test values? Turns out it doesn't matter. If anything, I think I'm going to plug my test values into this factor form of my inequality, because that makes my arithmetic a little bit easier. Yeah, but it doesn't matter. It should not matter which form of your inequality you plug your test values into. These 3 inequalities up here, the original that we have, this one that's set equal to 0, this one that's been factored, they're all equivalent. Okay, so I guess the next thing to do is plug test values into original. All right, so let's see. I'm definitely gonna run out of room here because these notes do not allow us, do not give us enough room here, but that's okay. So for instance, if I'm going to plug in x equals -5 into the factor form of the inequality. So if you think about it, so I'm gonna replace this x right here with -5. I'm gonna replace this x right there with -5. So I would say -1 times negative 7. So that's kind of what I'm doing. So here, so this one right here, that would say negative 1 times negative 7. And turns out that that is bigger than 0. Yeah, that is bigger than 0. So does that satisfy my inequality? Remember, my inequality is supposed to be less than or equal to 0. It doesn't. It does not. So this test value that came out of this test interval, negative infinity to negative 4, does not satisfy the original problem. So then that means that this is a bad test interval. This is not part of my solution. Yeah, so this test interval is not part of my solution. So that's why I'm crossing it out. Okay, now I gotta continue testing. Let me continue testing. Let me test x equals 0. So if I plug in 0 into the original inequality, and remember, I'm plugging it into the factor form, I would have 4 times negative 2. Yeah, so 4 times negative 2, and well, that's negative 8, which is less than 0. So that's good. That's good. What that says is that this interval satisfies my inequality. So the interval negative 4 to 2 satisfies my inequality. That one works. Okay. Lastly, I'm going to test x equals 3. Alright, I'm going to plug it into this factor form of my inequality. Well, that would be 7. 7 times 1. 7 times 1. Because if my x is equal to 3, that's 7. And this is 3 minus 2, so 1. So 7 times 1. And it turns out that that is bigger than 0. So that does not satisfy my inequality. So then that means that this interval right here is not part of my solution. This is not part of my solution. Okay, so then I think we have found our answer. We have found our answer. So the solution here, I hate my repertoire of color pens here. Solution. So the solution turns out is negative 4 to 2. That is the solution to the first part. Yeah. Okay, now let's think about this graphically. Now let's think about this little picture that I have drawn over here beforehand. So, okay, so we found the solution by doing what's called an analytical method. We didn't do any graphs, we just went through some procedures, solved some inequalities, tested some values. That's called an analytical method. We could have solved this using a graphical method. We just gotta understand what the inequality is asking us. On the left part of the inequality, of the very original inequality, I have the quadratic x squared plus 3x minus 5. And I'm gonna graph that. I graphed it in black. It's this little parabola. So x squared plus 3x minus 5, I'm calling it f of x over here. And I know how to change this quadratic to what's called vertex form. We did this a few videos back. You gotta complete the square here, and because I want to find the vertex so that I can graph it. I know that it's an upward opening parabola. I just want to know where the vertex of this parabola is at. And turns out that the vertex form is x plus 3 halves squared minus 29 over 4. That means that the vertex is at 3 halves. Sorry. So the vertex is at negative 3 halves, or negative 1.5, comma, negative 29 over 4. Well, negative 29 over 4 is negative 7.25. Well, that's the vertex down here then. Negative, so that's 0, negative 1.5. Anyway, so I sketched my quadratic. So this is my quadratic. And now, so that's the left-hand side of the original inequality. The right-hand side of the original inequality is x plus 3. That I graphed in blue. X plus 3 is just the equation of a line with y-intercept at 3 and slope 1. So the y-intercept is at 3 and goes up 1 and over 1, up 1 and over 1, and so on and so forth. And so I graphed both of these graphs together. I found the points of intersection. In order to find the points where these two graphs intersect, you need to set them equal to each other. And well, we kind of did that when we were finding the zeros. If you set them equal to each other and solve, you end up discovering that the points of intersection are when x is equal to -4 and when x is equal to 2. Those are the points of intersection. And now you gotta think, what is this inequality asking me? So what the inequality is asking you is, when is the right-hand side of my inequality bigger than the left-hand side of my inequality? So when is the right-hand side bigger than the left-hand side? When is the blue line bigger than the parabola, the black parabola? Or another way to think about it is, when is the blue line above the black parabola? And well, I have 3 intervals to think about: -infinity to -4, or -infinity to -4, the black line is above the blue line. That's not what I want. Right now what we're asking is, when is the blue line, the line, above the parabola, the black parabola? Well, it looks to me as though between -4 and 2, between x equals -4 and x equals 2, my blue line, the blue line, is above my black parabola. And then from 2 towards positive infinity, the black line happens to be above the blue line. So that's why I have highlighted the region between -4 and 2, because that's where the blue line, that's where x plus 3 is above the quadratic x squared plus 3x minus 5. See, in this region from -4 to 2, that's where my blue line is above this black little parabola. And that's what the picture is saying, yeah? So this is another way of solving this. I think I had mentioned to you Desmos earlier in the previous video, and I kind of want to talk about it a little bit again. You can also solve this inequality using Desmos. So let's see. Our inequality was x to the second plus 3x minus 5, and then in order to enter less than or equal, I'm gonna hit less. You can see that on your keyboard. You have to say shift, and it's like, I think, to the right of m, and then equals, the equal sign, and Desmos knows exactly what you're talking about. And then I'm gonna say x plus 3. And if you notice, Desmos just highlighted a little interval, the interval from -4 to 2, inclusive. Right now things are using parentheses because we're dealing with this type of inequality. So this would be a good technology to use in order to verify your answer. All right, so that's my answer. It's from -4 to 2, inclusive. Let's solve the next one. Let's solve the next one. Hopefully you have solved it. If not, pause the video, take a few minutes, see if you can solve it on your own. Okay, let's try to solve this little inequality. So the first thing I'm going to do, so I have x cubed minus x is bigger than 0. Luckily for us, this is already set equal to 0 in a sense. Now what I'm going to do is just factor it. Alright, so to factor, what I'm going to do is I'm going to factor out an x from both of my terms. So this becomes x squared minus 1 is bigger than 0. And I can continue factoring a little bit further. Turns out that I can factor this. It factors as x times x plus 1 times x minus 1. But let me just kind of erase a little bit of this stuff here so that I give myself a little bit of room and this is not such a mess. Bear with me. Oh, come on, eraser. Just work for me for once. If you're... Oh, lords of technology, bless me with the technology that works quickly and doesn't lag. Just give me 1 second. I just want to write down. Oh, anyway. So the factor form should be this: x times x plus 1 times x minus 1 is bigger than 0. That's what I should have. Okay. So that's my first step. And again, I have three forms of the original. Actually, I only have two forms of the original inequality: the original inequality and the factor form of the original inequality. And you can work with either of them. They should result in the same solution, whichever makes your life easier. Just okay. So we gotta find some zeros. Okay, so that means we gotta set our expression equal to 0. Alright, so that should give us three solutions. X equals 0, x equals -1, and x equals 1. Okay? See, now my eraser kicked in, but now I don't need it anymore. Now I kind of want to just write, but now I'm just going to be erasing. Hey, sorry. Let's see how long it takes for the red ink to kick back on. There we go. All right. Okay, so now we're gonna think about the test intervals. All right, so my test intervals are from -infinity to -1, and now I'm using parentheses. Why am I using parentheses now? Because of the type of inequality that I'm dealing with. This is a strict inequality. So -infinity to -1, I have the interval -1 to 0. I have the interval, and this, I'm not using union here because I'm not describing a domain or anything like that. I'm just thinking about this, in a sense, my zeros partition my Cartesian plane into several little parts, into 4 disjoint parts. And then I have 0 to 1, and then I have 1 to infinity. So those are my test intervals. The next thing I'm going to do is pick test values. Alright, so from each interval, let me pick a test value. So from this interval, I'm going to pick, I don't know, x equals -2. From this test interval, I'm going to pick the test value x equals -0.5. From here, I think I'm going to pick x equals 0.5. And from here, I'm going to pick x equals, let's say, 2. Okay. And then the next thing I'm going to do is I'm going to plug my test values into whichever form of the inequality that makes your arithmetic easier. Here we have 2 forms of the original inequality. This one unfactored, and then we have the factored form of the inequality. I'm going to be plugging things into the factor form. So plug test values into original inequality. Okay, so let me do that. So if I plugged in -2 into the factor form, so I'm using this form of the original inequality, the factor form, although it doesn't matter which one you choose. I'm just trying to make my life easier, and the arithmetic, I think, is a little bit easier if I plug things into the factor form. Well, then I'm going to have this -2 times -1 times -3. See, I'm replacing my x's with -2, so that becomes a -2, this becomes -1, this term, and this becomes -3. And so negative times a negative times a negative turns out is negative. Yeah, so what that means, and you remember our original inequality should be bigger than 0. And right now we ended up with something less than 0. So then that means that this test interval does not satisfy my original inequality. Alright, so let me test the next x value. So plug it into the factor form. So that becomes -0.5 times +0.5 times -1.5. Yeah, if I replace my x's in the original with -0.5, this becomes -0.5 plus 0.5 minus 1 times -1.5, And so negative times a positive times negative, that is going to become positive. So it looks like this interval, -1 to 0, does satisfy my original inequality. Let me test x equals 0.5. Well, that would say 0.5 times 1.5 times -0.5. That is negative. So we want to end up with something bigger than 0. So that does not satisfy my original inequality. And lastly, let me test plug in x equals 2 into my original. So that would say 2 times 3 times 1, which is positive. So this is good. So then my solution becomes this: -1 to 0 union 1 to infinity. Yeah, that would be my solution to this inequality. Now graphically what's going on is we have a cubic on the left hand side of the inequality, x cubed minus x. Turns out that if we graph that, its graph, well, looks like this little black curve here. It hits the x-axis at -1, at 0, and at +1. The multiplicities of all of the x-intercepts are odd, so we're always crossing the x-axis. Okay, and then on the right-hand side of the inequality, I have a very simple equation. The equation is just y equals 0. And y equals 0, well, turns out that that's just a horizontal line. It's just the x-axis. And so then what the inequality is asking you is, when is the cubic bigger than the horizontal line? Or when is the black cubic above the blue horizontal line? And well, the little black cubic is above the horizontal line between -1 and 0. That's why there's this little sliver right here. And it's also, the black cubic is above the horizontal line from 1 to positive infinity. And that's what our inequality is, our solution is saying. It's just capturing these moments where the cubic is above the horizontal line. Okay, so that is it for this part of 4.6. In the next part, we will graph rational inequalities, or we will solve rational inequalities. Solving rational inequalities is very similar to solving polynomial inequalities, just there's a little bit more fuss to it. Our test points are, there's probably going to be a little bit more test points to deal with, but it's a similar procedure. Okay, so I'm going to pause the video right here, and I'll see you in the next part. Thank you.